compatible operators. Suppose we have two operators A and B. Well, mostly they are going to be Hermitian operators, and if they commute, we call them compatible. Well, of course, the opposite is if they do not commute, they're incompatible. Well, this is just a definition, but it's a very useful language. Instead of saying there are two commuting operators, etc., this enables us to shortcut some of the language. So, well, let me give you some examples before proceeding and discussing the properties of compatible operators particularly. We have just finished a discussion on the spin 1/2 system. And what are the compatible example of compatible operators? For example, S squared and SC pair. It's just an example of compatible operators, but you immediately react to me saying that, well, you could also choose S squared and SX. That's also a compatible set. S squared and SY is also a compatible set. Well, this is the most fashionable one because usually when we take up solving the the common eigenvalue problem, we will choose these two. But any other two also out of these three is also very sensible examples. What about then what is the example from the same setting, from the spin 1/2 problem? For instance, SC and SX are incompatible because they do not commute, as you know. Or SC and SY, or SX and SY, any of these three within the same set, they also constitute incompatible operators. Now, we are going to now let's proceed. Well, if they are Hermitian, as always the case when we use this notation A and B, we reserve this notation to the Hermitian operator. We know that they have their eigenket bases associated with them, and this also has an eigenket basis. They are orthonormal and complete, thanks to the fact that they are Hermitian operators. And I'm not writing the definition. Well, one of them, AI, just to set the stage. That's the notation I'm using. It's slightly different than the notation used in the book because he uses primes, etc. It becomes a little confusing then. Well, I use the discrete set of indices. Eventually, we will move into the continuous spectrum problem. But for the time being, we assume that it's a discrete spectrum. And a nice example is the spin 1/2 problem we always refer to exemplify what we have been doing. Now, question is an interesting question when, in relationship with these compatible operators, how they are, well, I consider the case of compatible operators. That was just a definition. I proceed this discussion for the case of compatible set of operators, and I ask the following question. How are these two eigenvector sets are related in this case of compatible operators? How these two are related? Question. How these bases are related. I will proceed the discussion for the non-degenerate case. we'll consider non-degenerate case. Well, obviously, degenerate case, most of the things we will talk about will be valid in the degenerate case as well, but non-degenerate case is simple to handle as far as notation is concerned. Therefore, we will proceed for the non-degenerate case, and eventually we will comment and add some more comments in the case of degeneracy. As you all know, what is the meaning of degeneracy? There is one eigenvalue one AI. The correspondence is that for each eigenvalue there corresponds one eigenket. If there are many, one AI, many AI, that's non-degenerate. That's the degenerate, as you know, the usual definition. Well, the non-degenerate case is straightforward because remember we have also proven the orthogonality of the eigenvectors of a Hermitian operator associated with different eigenvalues for the non-degenerate case. Of course, we could also include the degeneracy into account, but let's proceed with non-degenerate cases. It's easy, otherwise we have to introduce a second index here, obviously. If there is one AI and many cats, obviously we are going to introduce a second index and it's going to complicate the life quite a lot, say. Let me not complicate the notation. You know what I'm talking about. Okay. Now we will prove a theorem for this non-degenerate case. That is, we start with two operators which commute among themselves. We assume eigenvalues of AR non-degenerate. Well, before proceeding for the B, if we have the eigenvalue problem defined as such for the A operator, the first operator, if you go to the matrix representation, as in the previous weeks that we have discussed, this will be AI delta ij. So this is diagonal, right? This is well known. And it's a very simple observation. What you do is take the eigenvalue equation, project it on another different eigenvector, and then use the orthonormality, and you get the delta ij. So this is the diagonal matrix in here. That's the form. Now the claim is, if so, AI B AJ is also diagonal. So that's the theorem. If they are compatible, that if they commute, then B in the eigenvector basis of the A is diagonal, and vice versa. A in the eigenvector basis of B is diagonal. That is, they can be diagonalized simultaneously. Compatibility leads to that, right? So it's a very trivial statement. Let's prove this quick give a quick proof of this statement. What do? We take the compatibility condition and then we take the matrix element of this operator equation between the eigenstates of the A. If it is valid as an operator equation, when you consider the matrix element, any arbitrary matrix element between AI and AJ in the A basis, you still get 0. Then what do I get? This x to the left gives me AI. In the second order, it's BA, x to the right gives you AJ. So what is left over is AI, B, AJ is equal to 0. You see, almost all the theorems in relation with these eigenvalues, eigenvectors are so simple. If you have a little bit of experience in the linear algebra, then some of these theorems may sound trivial. Indeed, they're trivially simple, at least if they are not trivial, but they are very profound. Being simple doesn't really, shouldn't let us think that they're really insignificant. They're very profound, but they're just simple. So what do I get from this equation? Non-degeneracy. This is an important assumption that we have started with. So single A eigenvalue, single eigenvector relationship is valid. So when we have this, we have the following two options. You may have this different than 0. The only way to satisfy this equation would be AI AJ is equal to 0, right? Then if AI is equal to AJ, then you can afford to have AI B AI different than 0. Then I set, if I set I equals J, then of course I have to consider this as second option, if AI is different than AJ, then AI B AJ is 0. Let's read these two statements together. When I is different than J, the matrix elements are 0, and when I is equal to J, that diagonal elements can be non-zero. Well, that's the definition of diagonality. Indeed, we have been able to prove that the B is diagonal in the A basis, and the opposite, not opposite, the parallel statement is you can take the A in the B basis, and you can also prove that it's also diagonal. Now let's proceed to write the B operator. Let's proceed again. We are still in the realm of these two compatible operators, A and B. Let me write, multiply the B from left by the completeness identity. By now you should be quite familiar in using this identity trick. That's the 1. That's also 1. Capital, these are identities, right? Not the number ones, identity operators. Completeness relationship. So what do I have? I have sum over I and J, AI, AI, B, A, J, A, J. Well, I haven't done anything. I have rewritten the expression by focusing on the inside. Now, we have seen from this previous theorem that B is diagonal in the A basis. and vice versa. You can repeat the same for the A operator. So this is BI, okay, delta ij AI B AI. Combining these two, you know that it should be diagonal, only the diagonal elements, and delta ij is telling you that when I is different than j, of diagonal elements are 0. This delta ij enables you to carry out one of these summations, which reduces a single summation. Then it becomes AI, AI, B, AI, AI. Okay. Now let's take this form of the B. It is a representation of the B operator in the A basis this way, okay? Using the previous theorem. Let's take this and act on, say, B AJ. I hesitated a single second. Of course, we should use different set of indices. I is a dummy index, now AJ. J is a free index, freely chosen. So what do I get? If I take this entire B and act on AJ, what do I get? I in here, A, AI, B, AI, AI, and AJ. This is the one I put all the way to the right and use the orthonormality, write it as delta ij, then carry out the I summation, set it equal to j, aj, a, j, b, aj. So what did I get? I get an eigenvalue equation, really. Well, we were expecting to get this, right? Notice that B is acting on J, reproducing AJ times a number. That number is the eigenvalue of the, if this is identified as an eigenvalue equation, because this acting on ket gives you the ket back times a number, this could be identified as the eigenket of the B with the associated eigenvalue. Okay. So this is the eigenvalues of B in the AJ basis. Eigenvalues of B in AJ basis. Okay. So how do I really express all these statements? If you call it BJ, so we see that A turned out to be a simultaneous, the AI we started with turned out to be a simultaneous eigenket of A and B. Of course, then this tells you that this notation may not be a fully explanatory notation, because we have chosen it from the A operator basis spectrum, but it turned out to be a common eigenstate of the B as well. So we have to generalize this notation to really make it more illustrative. That is, we generalize the notation to AIBJ, for instance, because it contains information vis-a-vis the B operator too. So a more illustrative notation is to use these two labels inside the ket. So this is indeed a correct simultaneous eigenset of the A and B. So if I act on it, if I act by A, I get AI AI Bj. If I act by B, I get Bj AI Bj. That is it. If so, then of course the eigenket should contain the proper information, and so we need two labels to make it more clear. Claim. All these, as I have stated in the beginning, all these statements have been proven for the non-degenerate case, but they hold for the degenerate case as well. These statements hold for the degenerate case as well. Of course, in that case, we will need additional label. What do I mean? For instance, AI, remember AI is the usual label that we started with before. It runs from 1 to capital N, for instance. There is another index which we may conveniently put up. So it means that is, I is the dimension of the space, ket space, capital N. It runs from 1 to capital N. And little k runs from 1 to little n. That is the dimension of the full space, dim of full ket space. This is the dimension of degeneracy subspace. Consider something we are going to discuss in detail in the future, but a known example, say, from your undergraduate education. Although we are borrowing it from the future, I have to illustrate this. A common eigenvalue problem of the orbital angular momentum, L squared and Lz. You have two quantum numbers to label these common eigenstate. One is the L orbital angular momentum quantum number, the other is the M so-called magnetic quantum number. And the states are degenerate, right? Because for given L, if it is already given, L runs from 0 to infinity in principle. So it is a discrete label, but infinitely many. But for given L, M runs from minus L to plus L. There are 2L plus 1. So the degeneracy subspace is 2L plus 1 dimensional. If L equals 0, it's 1. If L equals 1, it's 3 dimensional. If L equals 2, it's 5 dimensional. So when you have, here's a schematic picture. If this is the full Hilbert space, you have the degeneracy subspace filling this for the degenerate case. And how to handle those? Well, you put an extra label, and you sometimes hope that these extra labels are associated with another operator in which it is diagonalized. I think for the time being, that's sufficient for the orbital problem, because otherwise I would be borrowing too much from the future, because we are going to discuss those in detail. However, just as an illustration, I mentioned that there are cases of that sort. Okay, sometimes these degeneracy subspace eigenvectors associated with a different operator, B, may not be orthogonal to start with sometimes, but there is a well-defined, beautiful procedure called Schmitz orthogonalization procedure. We can orthogonalize it, then use it as an orthonormal basis after normalizing it. Okay. Well, as I said, the basic lesson, I don't want to get into too much detail, it's already clear from the orbital angular momentum problem, or from this A and B, that we have to use a set of collective indices instead of a single index. If they are associated with a set of compatible operators, A and B, we use the two eigenvalues to label it. If they are associated with more than two, there may be three operators. Hydrogen atom is again a good example, right? Hamiltonian is, the Coulomb Hamiltonian is one operator, L square is another operator, LZ is another operator. These three commute. And so compatible operators are Hamiltonian, L squared, and LZ. So they all commute among each other. Therefore, the common eigenstates that we construct, which are called the wave functions of the Coulomb Hamiltonian, labeled by the N, L, and M. Therefore, it contains three labels in the eigenstate, N, L, and M. How many? So the labels, the so-called good quantum numbers, are related to the number of compatible operators. If there are two, you have two good quantum numbers. If there are three good quantum numbers. More, although we won't see more, there will be as many. Now, question is an important question, as this course is based on very closely on this important issue, measurement. Measurement of compatible operators is the next subject I would like to take up. Okay. Suppose we, at the first level, we measure A and find the value AI. At the back of our mind, there's that beautiful setup, Stengerla gadgets. You see, all these things make sense, although it's just a two-dimensional vector space. Anyway, it's more general. The implications are more general than the two-dimensionality reflects in there. So you measure A. First of all, we are talking about compatible, so A and B commute, right? You find AI, then you carry out B measurement after this. You find BI, BJ. Use different indices so that we don't have the impression as if we are talking about the same thing. Then, after this, you repeat the A measurement again. Question. In the first one, you carried out a measurement on the A, you found little AI, and then you measured B, found little bj. Then you measure A, and you get AI for sure. Meaning that this interference, the presence of the second measurement operation, doesn't destroy the information you had before on the system. Thanks to the fact that they are compatible, you again get AI, not a different AJ or AK. So this tells you that second measurement doesn't destroy the previous information. Lesson. Second measurement. That is B measurement, right? That's the here. Doesn't destroy the previous information. It is kept at the memory of the system. So you measure it, you get AI again. Back. Get back this one. I wanted to use this language saying that whether it was there or not, when you get the same result, you say it's there. That's the reason why you really represent the common eigenstates with these two labels, saying that these two imprecise informations are possessed by the system under consideration. When there is degeneracy, okay, let me introduce that sort of rather more involved notation. All these are for the non-degenerate case. When there is degeneracy, then what happens? We label, first of all, say for A, or it may be for both. Let's suppose in the simplest case, A has a degenerate spectrum. Therefore, we represent the eigenvectors with a second label. There's one eigenvalue and many eigenvectors. So we carried out the measurements. A measure found the value AI. Then there are really many states coming out of it, which is CI, K, AI, K, BJ. I assume that, well, they're both compatible, although they commute. Therefore, a simultaneous eigenket should carry two sets of information. One is associated with the B, one is associated with the A. The A part is complicated. It is this. And B part is this. Instead of, okay. In the previous case, it was a single AI, but there are many states. Therefore, there are different states coming out of this, so all associated with the same eigenvalue measured. So what happens then? You carry out a B measurement to get, and you get Bj. So that selects what? That selects the AI K, still degenerate, and Bj. If you carry out an A measurement once more, you still get back AI. You see, the complication of the notation doesn't really spoil the basic principle that if you are carrying out a measurement, A and B consecutively, once you get an original value in the first measurement for A, whatever you do at the second step, regardless of it is degenerate or non-degenerate, you still get back the same AI. Notice that degeneracy means single eigenvalue, many eigenstates. There may be many eigenstates, but the value you get is unique, the same one as you have obtained in here. Perhaps I have to use a color to encircle it. Here. You still get back the same AI. Okay. Most of the things I have talked about is really, they are very simple, but yet very profound. Being simple doesn't really degrade any of the values that we talked about. The expressions is important. Now, what about the incompatible observables and measurement in the incompatible observables case? Compatible observables. That is A and B are not commuting. Well, of course, we can just reverse the argument and say that when they were compatible, they had a common set of eigenfunctions. So if they are incompatible, they wouldn't have a complete set of simultaneous eigenstates. Do not have a complete set of simultaneous eigenstates, eigenkets. I use those words interchangeably, right? Kets or states. That's the theorem, or claim, or lemma, whichever. That's the claim. Let's say claim. Sometimes calling them theorem would be too strong statements, right? They're mostly observations, which can be proven so easily. So how do we prove? The proof is, mathematicians use this argument very extensively. Assume the converse, assume the contrary, and show that it leads to inconsistency. Assume converse, contrary. Meaning, well, they have a common set of eigenstates. That's the contrary, right? The contrary to the original claim. We are trying to prove that they wouldn't have a complete set of simultaneous eigenstates. Suppose the contrary is true, we have A, AIBJ, AIBJ, and B, AIBJ, and BJ, AIBJ. So that's the contrary assumption. And then I multiply the first one with the B and second one with the A and subtract side by side. When the B is acting to the left gives me BA. And when it's acting to the left gives me AB. Let me use a different color so that I'm trying to save some time instead of rewriting everything. That's BA and that's AB. Whereas in the right-hand side, B comes, that jumps over this number, acts on the ket, gives you AI, BJ. And this A, again, comes to the right-hand side, jumps over the little b. It's a number, acts on the ket, gives you AI. So the right-hand side, I have AI, BJ. So these purple color second lines are what we obtain after the action of these operators on those equations. And then when you subtract these equations side by side, left-hand side is B, A commutator acting on AI, BJ. Right-hand side is AI, BJ, or BJ, AI. They are just numbers and they are the same. Right-hand sides are the same, so you get 0. If these AI, BJ assumed common eigenstate is an arbitrarily picked one from the spectrum, then if this is valid, when this commutator acting on that, it should be valid as an independent operator equality. You get AB is equal to 0. You get what? A contradiction, right? To the original incompatibility. Contradiction. That's the proof. If assuming the contrary, you get a contradiction, that's a nice mathematical type of reasoning, then your theorem should be true. So that assumption was not correct, so you don't have a common set of eigenstates. Let me illustrate this on a quite well-known, not illustration, exception. There's an exception. Sometimes you may have exceptions to these. It may be a bit surprising at first that such a powerful theorem, could there be an exception to it? Well, again, I will refer to that orbital angular momentum problem. Again, we borrow it from the future but you have seen at the undergraduate level, you know quite a lot about that orbital angular momentum quantum mechanics, well, let's borrow something from there. That's a very nice exception. Meaning, there may be some subspaces, not the entire vector space, ket space, but there may be some subspaces in that ket space in which the statement is not true as in its full form. Let me illustrate this, you'll see what it is. Consider the orbital angular momentum problem. What do you have? L squared and Lz is a compatible set of operators. They commute thanks to the algebra. But these are incompatible, for instance. These are compatible, and you work out the spectrum, and that's incompatible. Well, what are the states associated with this L and M? The L is associated with the L squared, and M is associated with the Lz. And you know that these are not, they're complete and orthonormal, first of all, because they are associated with this compatible set, complete and orthonormal. And claim they do not have a complete common eigenstate. Well, that's also true in its generality. However, if you consider the special case, L equals 0 subspace, the full vector space is, of course, spanned by these. And there are subspaces. There could be also L equals 1 subspace, L equals 2 subspaces there. This one is one-dimensional, this is three-dimensional, that's five-dimensional, etc. The entire space, as I have plotted before, is full of with these subspaces with changing dimensions. It is really essentially filled in by those subspaces. Focus on this L equals 0 subspace. That's one-dimensional, however. It's okay, 1D. Because 2L plus 1 is 1, just. So, what is the action of Lx on that L equals 0 state? How do we denote this, L equals 0 subspace? It is denoted as 0, 0, because if L is equal to 0, M is equal to 0, as I need two labels to be really straightforward, we have to use this legitimate full notation, 0, 0. That's a one-dimensional space. What is the Lx action on that space? 0. Ly is again 0. Lx, Ly commutator is Lz. Lz on there is 0. That's a very nice thing. So this is a simultaneous eigenstate of the Lx and Ly as well. So what is the lesson? 0, 0, that particular 0, 0, is a simultaneous eigenstate of Lx and Ly, despite the fact that they are incompatible, they do not commute, with same 0 eigenvalue, because right-hand side is 0, meaning 0 times 0, 0, right? That's an eigenvalue equation with 0 eigenvalue. So you see, you have to be careful. Although this statement holds in the entirety of the vector space, when you go to subspaces, there may be exceptions, and you have to keep your eyes open towards those exceptions. Now I will pick up the measurement problem in the sequential Stenger experiment setup again. So next I will consider, well, this was more abstract than general. Now I will consider the following. Stenger illustration, sequential Stenger experiments again. I say again because we have been taking this up whenever we have to really illustrate the problem in hand. Now this measurement of incompatible operators offers some interesting issues. The quantum, the quantum mechanical features of measurement theory is made more manifest when you really try to measure incompatible operators one after another. Remember, that was the starting point. We said, let's measure the z component of the spin in the appropriate Stenger setting. That was both a preparation gadget and an analyzer gadget. The first is a preparation gadget because it splits the beam, the totally initially unpolarized beam, into two, up polarized and down polarized in the z direction. So it prepared the system, and then you subjected to a second measurement, this time x measurement, and then etc. You repeated the same for the z. But the basic idea was we had incompatible set of operators, Sx, Sy, and Sc, and actually we were measuring those incompatible operators, and all the essential features of quantum mechanics was made manifest through that. So let's pick it up again in this new light and see what we get. So this is the break time, and then we'll continue with that after the break.